Howdy, everyone. Happy Friday. Congratulations to us all. We made it to the end of the third week of classes. This cartoon kind of is typical of what we have in quantum mechanics. We don't know exactly where things are, how fast they're going, and it's kind of like real life. There really are very few certainties about that. I have a question. Someone emailed me about this too. Can you use calculators or MATLAB on the homework? You can use whatever you want on the homework. The homework is primarily a learning process for you. And as you know, you will only get credit for effort. So we're not checking right or wrong. On the exams, you need to show your work. If you have integrals to do, you need to do it step by step. You'll find that most people get a lot of points from partial credit. So it's very hard to give partial credit if you just plunk down an answer. And so you can use calculators, but show all your work. Okay, so probability applies to real life and quantum mechanics. Okay, so just to remind you where we were last time, we're doing this nasty three-dimensional rotational problem, particle on a sphere, and this is most closely related to what we're going to talk about in atoms, which is going to be our next topic. Someone asks if I'm going to post practice exams for review. You have practice exams in your lecture notes. That's what you'll have. And you've got a lot of practice problems in the lecture notes. Okay, so please don't chat again for a while unless you have questions about the lecture that we're talking about. Okay, so we solved the three-dimensional problem, except that we fixed R. We found a lot of information about the quantum number L, the angular momentum quantum number. We also saw that we had M sub L's, and we related these to what we had in atomic systems. L sub L, or L0 being s orbitals, L1 p orbitals, and so on. And each set of those orbitals has different M sub L values. We also talked about the weirdness of space quantization. When you have electrons circling around nuclei, they can only do that in certain orientations. And that was proven by the Stern-Gerlach experiment. So now the good news, this is the very last page of the general quantum mechanics we have to cover. Then we can go on to systems that will seem more real, like atomic structure. So as you well learned in freshman chemistry, in addition to putting electrons into orbitals, you also had to worry about their spin. So I myself like to think about electron spin a lot like the moon going around the Earth. So with the moon going around the Earth, we have angular momentum going around more or less in a circular way. And then the moon itself is spinning around, and then the spin can add or subtract from the angular momentum, depending on which way you're going. And so we're going to have the same kind of thing when we look at electrons going around atoms. All right, somebody else has a problem question, and so I'm not going to take that. Just ask about the lecture. Towards the end of the lecture, I can take questions about problems or things like that. Problem sets are due today by midnight, and I think they can be uploaded onto eCampus. If you don't feel comfortable doing that, or if you have some problems, go ahead and just email your answers to either Dallas or Connor, one of the graders. Okay, as you learned in freshman chemistry, electrons have spin. We generally say they have spin up or spin down in freshman chemistry. In terms of quantum mechanics, there is a spin angular momentum quantum number. which for an electron is a half. And the total spin angular momentum is given by a formula which looks just like the formula with the L's for angular momentum, except here we have S's. So the total spin angular momentum for an electron would be a half times 3 halves, and then the square root of that times h bar. So this is the total angular momentum, but just as we had with angular momentum, it's going to have components. The components range from plus s down to minus s. The oddity about spin is the spin quantum numbers are halves. So m sub s can be plus a half or minus a half. In freshman chemistry, you probably talked about spin up for plus a half and spin down for minus a half. Let me remind you what I told you last time, that I used to spend 2 or more lectures on just these last few pages, and people just didn't seem to like it and get much out of it. So I've totally condensed everything we have down here into very small quantities. If you look at your book, you'll see something talked about as Russell-Saunders coupling. This is related a lot to the kinds of things we're looking at. But basically, we're looking at the kinds of quantum numbers and for angular momenta and spin that we're going to run into when we get into atomic systems. But the bottom line of all this is here in the summary. So first of all, we're going to have orbital angular momentum. This is the electron going around a nucleus. The total is given by J, as we saw last time, and in terms of the angular momentum quantum number L. We also have the quantum number m sub L, which can go from plus L down to minus L. And when we multiply m sub L times h bar, this gives us the angular momentum about one unique direction, which we call the z direction. Spin angular momentum, as I showed you up here, it's just s times s plus 1, square root of that times h bar. For an electron, spin is a half. For atomic systems, we can wind up with spins of 1s or 3 halves and things like that. Okay, so the complicated part, and this is the one that used to take at least 3 pages of notes, is the total angular momentum. So keep in mind the electron can be going around more or less in a circle, but we also have the spin momentum. So these things can combine, and we have a new quantum number, J, from which we're going to get total angular momentum. And J can have quantum numbers L plus S minus 1, and all the way down to the lowest absolute value of L minus S. So to be able to see what comes out of that, I've taken an example which would be L equal to 2, S equal to 1 half. So this would be like having an electron in the d orbital around an atom. So probably it's a larger atom. So notice with L equal to 2, m sub L can be 2, 1, 0, minus 1, minus 2. So as we all know, whenever you have a set of d orbitals, there are 5 of those with equivalent energy. The spin can be up or down, and we can write the spins as 1 half and minus a half. All right, well, what can J be? With L2, S equal to a half, J can be either L plus S or L minus S. So J can be 5 halves, or it can be 3 halves. So this is what will give us total angular momenta, and we can have atoms then that will have either this much momentum or this much total momentum. And then to further complicate it, the J's can have the m sub J components. These would be the components in the z direction. If J is equal to 5 halves, we can have all these components, 5 halves, 3 halves, 1 half, minus half, all the way down to minus 5 halves. So there's 6 of these components. So that would be one unique set of atoms with J equal to 5 halves. Some other atoms might have J equal to 3/2, smaller amount of angular momentum. Then it would have these components, 3/2, 1/2, minus a half, and minus 3/2. And now think about also when we talked about space quantization last time, this means that you're going to have specified orientations of the way that the electrons move around the atoms. And just as a final comment, if J is equal to 5/2, this will be the total angular momentum. If it's 3/2, this will be the total angular momentum. It'll be less. As I've said before, physicists love to study excited state atoms. They can pick out exactly what quantum states they're in, what kind of angular momentum they have. They love to smash them into other atoms, see what happens, look at dynamics, things like that. But chemists, maybe even more so chemical engineers, generally don't care about this stuff, so I've reduced it quite a lot. Okay, next thing you'll find in your notes are what I call practice problems 1. So these cover particle in a box, harmonic oscillator, rotation, and the hydrogen atom, which we have not yet talked about, but will be talking about. So you're asked to do something with each of these, and I give you answers for all those. And so then after the answers, I also have a set of problems called more practice problems. One is in general about wave and particle properties, then the photoelectric effect, Compton effect, and then once we get to atomic spectra, about atomic spectra. So this is your best study source when the first exam comes. That's still, I guess, 3 weeks away. Yeah. So you've got quite a while to study, but don't get behind on things. Be doing these problems all along. You can't cram this stuff at the last moment. Okay, so that finishes basic quantum mechanics background. So this now brings us to atomic structure. And in fact, the topic is atomic spectra and atomic structure. And first I want to talk about the spectra that you get from atoms. And so I've scrawled out this cartoon-like image of how the first spectra were taken of hydrogen. So as we all know, hydrogen is a diatomic molecule. It exists as H2. Here I've stuck it into a flask, and I'm shooting an electron gun at it. And some of the hydrogen gets split apart into hydrogen atoms. Those hydrogen atoms are generally going to be in excited states. So in other words, instead of having its electron in the 1s orbital, they might be in the 2p orbital or the 4d orbital, something higher up. And then when the electron decides it wants to go to lower energy, it falls back down. And we have delta E equal to h nu. And so we have light coming out. So here's emission of light. In the early days, in the late 1800s, people put this through a prism. Different colors would come off at different angles. And people would look at then what frequencies and wavelengths of light had actually come from the hydrogen atom. So here I've shown a photographic plate. Nowadays, we have spectrometers that do it in a much more sophisticated way. But this is the way that the early experiments were done. And I think I have a picture in the notes of the spectrum on a photographic plate. So the prism obviously separates the frequencies according to the angle. Okay, so here's again my basic same picture. H2, electrical discharge, or hitting it with electron guns, splits it into hydrogen atoms. And this is going to emit, I've written ultraviolet light, but I was a little bit too narrow in saying that. We actually get light in the visible range, which was observed first, and we also get light in the infrared range. So low frequencies in the infrared all the way up to ultraviolet frequencies are observed. Okay, so this was already observed in the late 1800s, and then people were puzzled, why in the world is this happening? But ultimately, based on information I'm about to give you, Rydberg and Ritz came along and developed what got to be called the Ritz equation in 1908. And it said that the reciprocal of the wavelength, which in fact we can call a wave number, it's the same unit you used in organic labs for infrared spectroscopy. So in centimeters to the -1, it's given by a constant called the Rydberg constant, which is quite large, as you can see, 109,000 something wave numbers, times this difference, 1 over n1 squared minus 1 over n2 squared. And n1 and n2 wind up being quantum numbers. As we're going to see later, these are going to refer to the principal quantum number that you learned about in freshman chemistry. So if you had a 2p orbital, n was 2. If you had a 1s orbital, n was 1. A 5d orbital, n was equal to 2, and so on. Anyway, at this point, people did not know what atoms looked like, but they were able to fit this kind of spectrum. Okay, so where did Ritz and Rydberg come up with this equation? Well, the first person to really contribute to this was a fellow in 1885, as I pointed out, J.J. Balmer. He was in Switzerland, and he was a high school math teacher. And he looked at what we now call the Balmer series, and it wound up being the series where n1 equals to 2. Basically, why this was looked at is because this gives light in the visible region. It was most commonly understood. They could see it through a prism. They could figure out what the wavelengths were. But Balmer played around with the numbers, and he was able to come up with this formula. Now, it might surprise you a little bit that a high school teacher would come up with this formula. So this is 1885. All of you know, of course, Texas A&M was founded in 1876. But do you know how many public high schools there were in the state of Texas when Texas A&M was founded? So send me some chat answers and we'll see what you think the answers are. Okay, I'm getting an average of somewhere around 100. The answer is 0. There were no public high schools in the state of Texas in 1876. There were some private high schools. So I think in 1876, when Texas A&M opened, 4 students began. I haven't read enough about their history and whether it's even written, but presumably they were homeschooled or self-taught or whatever. And they came on to Texas A&M. There were private high schools that you had to pay for. So I don't know how many of those were, maybe even a few dozen or something like that, but there were no public high schools yet in the state. Okay, so Balmer came up with this formula, and how is this related to the Ritz equation? So I'm going to take Balmer's formula, and I'm going to divide through first by n squared. So we'll take n squared out of the denominator and out of the numerator also. This is what we wind up with. You'll see it'll be 1 minus 4 over n squared. So if I flip this upside down, you will see that this will look a lot like the equation that I have up here. In Balmer's case, the n1 wound up being 2, so n1 squared is 1 over 4 when we put it here. Remember again, Balmer's formula was for lambda. The formula I'm giving you here is for 1 over lambda. Well, this was a big deal because you remember we talked about Newton, and when Newton came along, uh, people didn't realize that mathematics and science went together and you could start predicting things. And now this was the way that we get into quantum mechanics. People understood that there were unique things about atoms that could be learned by studying their spectra. So I apologize, for some reason the PDF version that I have doesn't allow me to rotate this. I have a second version, but it blinks out on me, so I don't dare use it for class. But this is then a photographic plate that we have. Here's the wavelength in nanometers. Visible range is roughly 330, well, it's shown right here. It starts at 400. Actually, I made a mistake. Normally people say it starts from 370 up to about 700 nanometers. This shows it slightly shifted, but it's going to depend exactly on your own eyeballs and your own vision. Okay, so you'll see there's light down here. This is infrared region, this is visible, and then there's some lines up here. And then the 4 diagrams here, these are probably all just taken off of this bigger one so we can name the series. The Bomber series is this one right here. So this is in the visible region. I've written on top here what some of the transitions are. This one is 3 to 2, this one is 4 to 2. So what we're going to be seeing, this line right here comes from an electron in an n equal to 3 atomic orbital on the hydrogen atom, maybe the 3p orbital, falling down to the 2s orbital or something like that. Then the next one would come from n equal 4 going down to 2, maybe the 4p orbital down to the 2s orbital. And then you get a bunch of others, and then they finally end at some point. So the next one here would be 5 to 2, 6 to 2, 7 to 2, 8 to 2, and all the way up practically to 1,000 to 2 or whatever. But maybe something like 30 or 40 of these bands can be seen. Okay, well, it turns out that, as you can see, there's also bands in the ultraviolet region. These are called the Lyman bands. And so this is a 2 to 1 transition. The Lyman series always ends on principal quantum number n equal to 1. So 2 to 1 is quite a lot higher, because we're going to see the 1 level is very much lower than all the others. 3 to 1 is higher yet, and these are kind of faded out in my slide here, but you can see there would be 4 to 1, 5 to 1, 6 to 1, and so on. Okay, so Lyman explained these, then Paschen comes along, he gets another series named for him. Brackett comes along, he names those. Possibly people like Paschen and Brackett actually observed these bands and were able to explain them. There's another series called the Pfund series, PFUND. I'm trying to remember what the next one was, Huygens or something like that. Anyway, lots and lots of series were observed, and once enough of these series had been put together, then Ritz and Rydberg realized that this could explain every one of those bands. I'm going to mention this at least 100 times to you, but the main message of this is going to be that the energy of each hydrogen orbital is simply going to be minus R sub h over 1n squared, where n is the quantum number that we have. Okay, let's see if we have some relevant chats. Someone says, why are there clear emission bands if is there no interference between the photons? No, they're distinct transitions from individual states. It's very much like all of you, wherever you are, you can get your own cell phone telephone call based on your own frequencies involved, and so they aren't interacting with each other as they're emitted from these systems. So any individual atom is going to be in one specific quantum state. When I show you a spectrum like this is a spectrum from jillions and jillions of atoms. One atom will only give you one photon at one specific frequency. Okay, so this is what I just summarized for you. Balmer was the first one, ending on n equal to 2. And then we had Lyman, Paschen, Brackett, and then the Foote series. Now, unfortunately, I think the Atkins physical chemistry book is still the best one available, but over the years have decided to drop out the original explanation for the hydrogen atom that was presented by Niels Bohr. So Bohr, based on this Ritz equation and the spectra and everything, came up with a model of the hydrogen atom that could exactly predict what the spectra, these spectra right here, exactly what they would be. So it's quite an impressive event. Yeah, it says Bohr did this in 1913. A few years later, he got the Nobel Prize for coming up with the first model of the atom. And what you will see is the Bohr model of the atom, even though it won't be exactly correct, this is typically what you still see on charts in high school chemistry laboratories. It'll show an electron going around an atom, a nucleus in more or less a circular orbit, and it'll show that there are different orbits with different energies. One of the problems in your book, I don't think I assigned it, will ask you to look at the Bohr model of the hydrogen atom. It's no longer called 1315. Atkins has renamed all his problems according to this crazy way of E7 dash whatever, instead of just nice numerical system. Okay, so here's the Bohr model of the atom. And one reason I want to show this to you, in addition just to the historical context, is that we're going to get a definition which we're going to call A0 out of this. We've already been doing quantum mechanical calculations that we've done in the last couple of weeks in class, and you run into the fact we've had something like e to the minus r over A0 or something like that. And A0 is called the Bohr radius. The Bohr radius is what Bohr predicted would be exactly the distance that an electron would be from the hydrogen nucleus in its lowest energy orbit. Well, we're going to find that that electron moves all over the place. It's not stuck at A0. It's going to be all over the place. But its average value, its most probable value, is in fact going to be A0, which comes out to be about 0.5 angstroms. Typical carbon-hydrogen bond distance, just for comparison, is about twice that. Okay, so Bohr says we have an electron going around the positive nucleus at a fixed distance r. And he said, since we're seeing individual frequencies between the different energy levels of hydrogen, we must have quantum states. And he said the angular momentum is quantized. We've already seen in what we just discussed, angular momentum is linear momentum, mass times velocity, times r. And Bohr said it's equal to nh bar. Now notice this is exactly correct for what we wrote for J sub z before, but it's not correct what we got for total angular momentum. So you might think that everything's going to fall apart for Bohr since he doesn't quite start off correctly. There really aren't circular orbits, and he doesn't quite have the angular momentum right. But Bohr knows what the answers are from Balmer and Ritz and Rydberg and all these things. So he can adjust his data to make everything work out correctly. And that's why he comes up with J equal to NH bar rather than the correct one. Okay, well, part C is correct. Bohr said the Coulombic force of attraction is this. So just as a reminder, what you learned in physics, the force of attraction is the product of the charges divided by the square of the distance between them. So here we're going to have a proton in the center of the atom, an electron going around it. And just to make this more generic, I'm going to write this for not only hydrogen, but for hydrogen-like systems that have one electron. For example, helium plus will have 2 protons in the center, and that's what I mean by Z equal to 2. Its atomic number is 2. But if it's helium plus, it's lost an electron, so it'll have 2 protons and 1 electron. Lithium plus 2 has also been studied. It has +3 charge in the center, but lithium plus 2 has only 1 electron around it. So I'm going to stick the possibility that our nucleus is going to have a charge Z times E instead of just E. So E is the electron charge. So that's easy to remember and understand since we're talking about an electron. The electron has a charge of minus E, but the charge of a proton is plus E. If we have the hydrogen atom, Z is equal to 1. And so we just have a plus E charge. If we have the helium atom, Z would be 2, we'd have a plus 2 charge. Let me jump ahead and just so it's clear. Okay, so this is what we're talking about. Hydrogen has Z equal to 1, helium plus has Z2, lithium plus has Z3. So we'll come back to this page later when we look at the other possibilities. Okay, now here I want to point this out. You remember I talked last week or earlier in the week about force constants. Your book uses newtons per meter, which I think is kind of silly for very short distances, and most spectroscopy people, molecular structure people don't use that. The book sticks strictly to internationally accepted units. And so the book is going to have a different unit for force. The book is going to use newtons to talk about force. I'm going to use it in atomic units. Now I have a chat question. Let's see if it is relevant. Okay, request to zoom in. That definitely can be done. We'll zoom in a lot. Okay, so notice the difference between my formula and the book formula is 4 pi epsilon naught. This is called vacuum permittivity, and I'll talk about units later, but basically vacuum permittivity is a unit that converts coulombs into joules when we're talking about energy. And it also shows up here. Now, the reason I and many people don't like to use it in these kinds of derivations is you wind up having to manipulate this term. Sometimes you have to square it, but it's basically just a conversion factor. So we hate carrying around things like 16 pi squared epsilon naughts. So I hope you're just happy if you just stick with my model of attraction that I've given right here. So this model agrees with that one also, except it throws in this crazy conversion unit. So we're not going to use 4 pi epsilon naught. Okay, so you should have learned this electrostatic attraction from physics. You probably also heard about centripetal force. So the centripetal force, if you have something going around in a circle, is given by this formula here, according to our physics books. And so what Bohr said was the electrostatic attraction has to equal the centripetal force. And so he equated these two formulas here, and he wound up with a formula for velocity. So solve for v out of this mv squared situation here. And then Bohr had his angular momentum condition, n is equal to h bar. It's equal to linear momentum times the radius of the circle. And when you plug in what the velocity is from here, then you come up with this formula and you can solve for r. So Bohr's conclusion was that you can only have certain radii for the hydrogen atom. And he came up with a quantum number n, and it could be 1, 2, 3, 4, etc. So it's going to turn out this is exactly right, the fact that we can have quantum numbers n1, 2, and 3. And in fact, this is going to lead to the correct energy that we have for the system. What we're going to find is if we do put n equal to 1, and this, for example, would represent the electron in a 1s hydrogen orbital, that will be equal to the Bohr radius A0, and that will be the most probable distance that the electron is far from the nucleus. Okay, so here I'm just reminding you, if you write 1s, 2s, 2p, 3s, the integer number tells us what the quantum number is. Okay, a lot of chats. Okay, nothing useful. Someone must be leaning on their screen or something. Okay, so as I said, if we evaluate then what we get for z equal to 1 and n equal to 1, so this is a hydrogen atom, n equal 1 orbital, this magnitude comes out to be 0.5292 angstroms, which is 52.92 times 10 to the minus 12 meters, or 52.92 picometers. I don't know what you've used in chemical engineering. Chemists tend to still like to stick to angstroms, but if you like picometers, anytime I say angstrom, just multiply it by 100. But this A0 value, which you can see is this h bar squared over me squared, is something that proves out to be very useful in all the wave functions that we're going to have for the hydrogen atom and larger atoms. Okay, so I promised you that Bohr got the correct energy levels. And so how did he do that? He said, well, the electron's going to have kinetic energy, 1/2 mv squared, and it's going to have a potential energy. And so the attractive potential energy is given by this. So again, this would have that vacuum permittivity in there. A term like this, if I wanted to have the units be in joules, but we're going to do this in atomic units. Okay, so here's Bohr's formula for that. He's already given us a formula for velocity. He's given us a formula for R. So it's just a matter of plugging this in. I'm not going to go through this step by step, but when we put it all together, it turns out that this is absolutely correct for giving us what the energies would be for the N1, N2, N3, etc. orbitals. So just to relate it to that, the Rydberg constant, R sub h, that I gave you, was found to be this, E squared over 2 times n squared, n being 1, uh, and hc. hc is a conversion factor that gets us into centimeters to the -1. And don't worry about units right now. I'll try to review them all later when we have to work with these things. But if we want it in wave numbers, we have to put an hc in there. Right here, this simply would come out to be in joule units if we worked it up there. Okay, so this meant that every energy level for the hydrogen atom would be given by this formula right here. So Hc is a conversion factor, Z is what we might have to modify it if we have helium ions or lithium ions. But all of the energy levels, excluding the fluffy conversion factors, they basically come out to be minus R sub h over n squared. So this part probably isn't even necessary, but if we wanted to then know the energy difference between two states, delta E would be, we stick in one n value for the upper state, a lower n value for the lower state, say that's equal to h nu from one state to the second state, and then it would come out looking like this. If I want to go into wave numbers, and you'll see here, then I'm going to subtract out, factor out the speed of light. Notice in the first case, I'm factoring out the h in the hc that I had, but then to get it into wave numbers, I divide by c. So this would be the formula according to Ritz that we have. We're going to look at this in terms of the Schrodinger equation again. So if the conversion factor stuff confuses you right now, I'll get into that a little bit later when we do it. But when this was completed, the scientific community was totally amazed. And as I said, they gave Bohr the Nobel Prize for it, because he absolutely perfectly predicted what the energy levels would be, and therefore all of the transitions could be seen. So here is our typical energy diagram, energy going up. Every horizontal line represents a possible atomic orbital that you have on the hydrogen atom. Now notice on this picture, I'm not differentiating at all between s, p, and d orbitals. We'll talk about that later. But for the hydrogen atom, it doesn't make a difference what the quantum number L is. So s, p, d, f orbitals all have the same energy in the same shell. So if we're at n equal to 3, which are if we're at n equal to 3, we could have s, p, and d orbitals. The d orbitals would have exactly the same energy as the p and s orbitals. Okay, so look at the lengths of these arrows. The Lyman series was in the ultraviolet, so they're the greatest transitions. As always, delta E is equal to h nu. So the energy difference, for example, for the N2 to N1 Lyman series would be starting from minus 27,000 going to minus 109,000. So it would be about 82,000 wave numbers. I should have pointed out the convention here is that E0, which occurs when the quantum number n gets to be infinity, the energy of 0 is when the electron has totally left the nucleus. And then when the electron is still on the nucleus, that's how much it is stabilized by getting down into this orbit. I'll mention this later, but the ionization potential of a hydrogen atom would be exactly the Rydberg constant here, because you would have to take the electron from here at minus 109,000 wave numbers, take it up to 0, and so that is the ionization potential. Comes out to be 13.6 electron volts is equivalent to that. So we can play around a lot with units. Because we're going to be at the atomic level, we'll use wave numbers a lot. 350 wave numbers is equivalent to 1 kilocalorie per mole. I think it's 83 wave numbers is equivalent to 1 kilojoule per mole. And 8,000 something wave numbers is equal to 1 electron volt. So we can jump around in these units quite a lot. Okay, then also notice the Balmer series the arrows get a lot shorter. These wind up in the visible region. Paschen series wind up in the infrared. And when you go higher and higher up, you can see closer and closer levels. I actually have a colleague in Switzerland who loves to look at higher Rydberg states, not only in atoms, but you can look at them also in molecules. And he's looking at things like going from quantum state N45 down to N44. And so these are going to be very, very low frequency transitions deep in the infrared region. So this extends quite a lot. Okay, so again, the scientific community was totally dazzled because now they had an exact mathematical formula that they could understand to predict the energy levels. So let's go back and look at that formula. You'll notice what we have here. Well, I've written in terms of A naught, but it takes the charge of the electron, which was known. Oh, okay, I've written it right here. So the charge of the electron and the mass of the electron come into play here. Those were known quantities, and because Bohr could use these quantities simply by taking fourth powers and so on, and come up with exactly the number that had been observed experimentally, people were just really amazed that atoms were now finally understood for the first time. Okay, so I put a prettier picture in your notes. It's basically the same picture. It tries to equate the spectrum more carefully here where the transitions are. And so the highest transition you can see is when you're going from virtually n almost infinity down to n equal to 1. This transition right here is the 2 to 1 transition. This transition is the 3 to 2 transition. This one is the 4 to 3 transition. And then the next ones will end on 4 or 5 and so on. Okay, notice on this diagram, they've labeled the E as a minus E. And they've also rounded off the number 109,677. They've turned into 80 as such. And notice here again, R is written in terms of just parameters that people had known before. Also notice in this case, they have used the vacuum permittivity. That's why we have this 8 epsilon naught cubed in there, just to make life messier for us when we're trying to do a computation. Okay. Now here's kind of a summary of what you might have seen on your high school chemistry lab wall. Bohr imagined you have circular orbits. This diagram isn't quite to scale because if you look at the Bohr formula for bond distance, and excuse my scrolling back and forth all the time, notice that Bohr says that R is proportional to the square of n. So if you go to n equal to 2, it should be 4 times farther away than n equal to 1. If you go to n equal to 3, it should be 9 times further away. And we're going to see, once we look at how Schrodinger treats this problem, that things are going to follow that kind of trend quite closely. So whoever drew this picture drew it just in a way to make it pretty, have concentric circles equidistant from each other, but N2 should be 4 times as far away as 1, and then N3 should be 9 times farther away, and so on. But this shows the Bohr model that you can have absorption spectra. If you have hydrogen atoms, you shine light into it. You can kick electrons from N1 to 2, from 1 to 3, 1 to 4. You could go from 2 to 3, 2 to 4, and go up. The photographic plate that I showed you, kind of a poor man's facsimile here, would be transitions like this, going from 2 to 1, 3 to 1, 4 to 1, and also you could land at higher levels. So these are shown in the diagram here. So a lower frequency, longer wavelength for the first transition, higher energy for the next one. You can see this starts getting to be higher frequency, next one higher frequency yet. So this might be the way a high school chemistry book represents what's going on if you would have talked about these things at all. Okay, so I keep telling you, and I guess we're out of time, so I'll just tell you what we're going to talk about next time. Next time, we'll see how Schrödinger treats the problem, and it's a doable, exactly solvable problem in one dimension. Electron going around a heavier mass. The proton is 1,832 times heavier than an electron. And so we can just look at what kind of orbit the electron is going to have, what kind of energies. We're going to see we get a bunch of wave functions. You'll notice these are going to have a lot of A naughts in them. But at this point, I will stop and wish you a happy weekend. And if you have any questions, let me know. Okay. Fellow that sent us a lot of zeros apologizes. He has a crazy keyboard. Okay, stay healthy, everybody.
Dr. John?
Yeah, is there a question?
Yes. When we're finding the maximum for a probability density function, do we have to prove that it's a maximum by taking the second derivative and doing the concavity test, or can we just get away with doing the first derivative and setting it equal to 0 and finding it that way?
Okay, your mic has a lot of echo, but I think I understood the question. If you want to find the maxima or minima in a probability function, the probability function is psi star psi, which is usually psi squared. You take the first derivative of it, and that will give you the maxima and minima. So some will be nodes where the probability is 0, the other will be maxima. In calculus, you learned if you wanted to differentiate between them, you would have to take a second derivative. I think in your problems, you can tell yourself whether a particular point is going to be a maximum or minimum just by looking at the sine function or whatever you have. So you don't have to go beyond that to prove it. I think you can even identify where the nodes are just by looking at the trigonometry of the problem. You know where sines go to 0 or cosines go to 0. So you can identify your nodes even without taking the derivatives. And then the other things that come out of the solution will be your maxima. Was that what you were asking?
Yeah, essentially. And also, if we get that it's a maximum for n pi, is n equal to 0 included in the solution set?
Okay, there's just too much echo for me to understand you. Either send me a chat if it's a quick question, or send me an email and I'll answer you right away. Okay? question, I'm not sure what kind of problem you're looking at. It says if n equals 0, or when x equals n times pi is included. It depends which problem you're looking at. Translational levels don't have n0. Harmonic oscillator functions do have n equals 0. We might be looking at a particle in a circle. But it should be pretty intuitive if you remember your trigonometry and calculus. If you look at the functions you have, which I assume are sines or cosines, that you can tell where the zeros are. The maxima, maybe even intuitively, you could tell also that cosines are maxima at 0 and 2 pi and things like that. But by taking the first derivative, you'll get all the answers. Write me a longer email if that's still not clear. Okay, so have a good weekend.